Hi, my name is Christian. I had a similar talk last year at ContainerDays talking about HPC and AI, or big data and big compute. This time around, it's a slightly different version. I would like to talk about, at the end, it evolved. So I would like to talk about how we forget in ContainerDays, in Containerland, to optimize for hardware again. And I will talk about this in a sec. So about me, I used to work for Docker, I used to work for PlayStation Now, and I'm going to start at AWS next month and next Monday. So I still have my old t-shirts because I don't have the internal merch yet. I'm wearing off what I have from Docker, but it's, I think, a nice journey. And I started in automotive back in the days, so that's why I'm prone to high-performance computing. Okay, so the agenda is as follows. I will talk about a little bit about what big compute and HPC, how it went through changes the last couple of years. Also how science changed over the time, and how this is fostered by the rise of AI and ML, or what fostered the rise of AI and ML. And at the end, as said, I would like to talk about how those two science research applications merge together and will hopefully change a little bit how we do containerization in the end. Okay, commoditization of big compute. There is a top 500 list of the fastest and biggest toys in the world, the biggest systems to do tightly coupled workloads, which is like weather and weather forecast, climate research, nuclear stockpile stewardship stuff, so how to test atomic bombs without testing them, and so on. And they have a list over the last 25 years, or almost 30 years. And this is just a couple of statistics out of this list. So this blue line here, this blue box at the left-hand side, from your perspective, is the clusters. So we have now commodity clusters, which is just a lot of pizza boxes connected together with a nice, fast interconnect. But this trend is clear the last couple of years, 20 years or so, or 15 years, that we go to Linux boxes, and Linux boxes on the right-hand side. We see this reddish dominance. This is just the amount of, or the share of Linux systems within this top 500 list. So we are now at Linux, and we are now like Linux clusters, and this is exactly also what hyperscalers do, right? They have a lot of boxes, and they have a lot of Linux. From the CPU or processor side, this is dominant nowadays by x86, but this is challenged, of course, due to the GPUs, rise of GPUs and all this, by accelerators. And even CPUs are challenged as well. x86 is not dominant anymore in HPC. In the next couple of years, we will see ARM, we will see special ARM implementations by the Chinese, for instance. We will see Vector again in Japan, and this is going to be more diverse over time. And some call it the Cambrian explosion of accelerators. So there are 40-ish, a little bit more than 40 AI accelerators in development currently, or as project in development. And I mean, this was going to be crazy. But Linux is here to stay, clusters are here to stay. How they are computing is maybe a different story. And also, one result of this convergence and also this drive from the enterprise side is that everything is commoditized nowadays. So data centers, hyperscalers like Google, AWS, Facebook, they redefined how large scale is done. They have this open compute project which has slightly wider racks with a power bar at the end, so you don't need to plug any cables anymore. You just put it in. It doesn't have any power supply. It just plugs right in, which is pretty nice, which is not adopted in HPC systems as of today, somehow weirdly. How systems are operated, the DevOps movement redefined this as well, working more closely with software developers so that it suits them and is not just what the silo operations defines. Same goes, of course, for software developers with CI/CD and this DevOps movement where they talk to operations. They redefined a lot how software is developed and also released. Storage is a little different in HPC, and also I think in normal operations. The death of POSIX is a long time coming, and somehow it didn't come. So fast POSIX file systems are still something where HPC thrives and where HPC has a stronghold. But object stores are more and more commoditized by the non-HPC players. We have Ceph, we have S3, and we have this API that a lot of people use. So that's going to be interesting how this plays out. But the Linux kernel, as I showed, is everywhere now. And with Linux kernel virtualization, which we call containers, the technique is available, and a lot of people slowly getting into it. Scheduling is as well not yet a commodity in HPC. Non-HPC is already a commodity as well. So you have like Kubernetes, you have Swarm for smaller installations maybe, and you have Mesos. So, and maybe everyone is using Kubernetes anyways, but in HPC is a little bit different. So this slide is just commoditization drives HPC guys. And normally the HPC guys were the spearheads of innovation, so they innovated the clusters thing, like Linux clusters. That's what they did. And also HPC is like 50-year-old or 60-year-old discipline or thing in the world. So they were used to have the big money and the big machines, but nowadays a data center of AWS or Facebook is like 1 billion, and that's not what they can compete with. Anyhow, this is also accompanied by a change in science. So we had, maybe we do this instead. We had a paradigm shift over the last couple of 100 years, and of course accelerated by recent developments. The Greeks, they thought long and deep about theories, but they didn't really check the theories maybe, and this is like, I'm not a historian, but that's like a very blunt like idea. Galileo was stubborn and insisted on facts based on science doing experiments, so he created this little telescope, and then he thought, oh, maybe there's something different from what we think, and he insisted on it and like based or started to mix theory with experiments. So you think about it something very hard, then you conduct an experiment to prove your theory, and at the end, in like 200 years ago, 150 years ago, Humboldt, he formalized it into a method for education and science, so that you have like you learn the basics, you try something, you think a little bit about stupid things, and then you try to prove what you thought is worth proving. And this, of course, is now accelerated by simulations. So I think fair to say, like the Second World War sparked this increase in computational power. And shortly after, we needed to simulate like weather, we needed to simulate nuclear stewardship, like nuclear piles. And what they did back then was using small data, like historical weather data, for instance, and do hindcasting, which is a nice word. Like forecasting is predicting the future. Hindcasting is using the day before yesterday's data to predict yesterday's weather. And you have like this is an experiment you can conduct. So it needs data as well. But of course, with big data now, you are not doing first principle simulations, like you don't think about a theorem and then you try to compute it. But you have a lot of results, and you try to think about a theory that might be derived from this result. And this is what the computer does for you, and that's what we call AI, big data today. Okay, and something else that is ongoing and that changes science as well is the so-called computing continuum. So we have the big centers at the very right. There are only a couple of them, like the top 10 systems. They are very expensive, like 1 billion or a couple of 100 million, but there's only a couple of them, but the size is huge. And then we go through smaller and smaller clusters, smaller and smaller installations to the very left-hand side, where we have little Arduinos that we can just throw out because they are so cheap. And we have this edge fog and big system continuum where we need to do compute, and we don't want to program it for all the different things. We want to do it once, maybe in a container, and then we want to apply it to different styles of computation, let's put it this way. So, and the left-hand side is very simple and fast evolving. The right-hand side, maybe not so much because it's more expensive to buy it. And of course, this thing was not working, I guess. And of course, the mobile phones we carry around, they are somewhere in the middle, I guess, from the computational power. And yeah, they are also in the mix, creating a lot of personal data and creating a lot of data to chunk. And this too slides are based on these two presentations, and there's a lot of stuff you can go through if you search for those. They're very nice presentations as well. Okay, the rise of AML. We have two things that contribute to the rise. First, we need data to do big data, and these data lakes are, of course, pretty much served and filled by the cloud. So the cloud basically rains into the data lake. And the IoT is also contributing to it, and little devices like smartphones, of course. So we have a lot of data that is laying around, which we didn't have before, and which was hard to gather like 20 years ago. You could not get this amount of data. And also with this data, we can do actionable things nowadays because we have a lot of computational power that is provided by GPUs in the first place, but then through AI accelerators like TPUs, and there are a lot of other vector accelerators that help there. So we have the data, we have the computational power to do something with it. So we have the dragon and we have the fire, so to speak. And this is what also helped AI and ML get off the ground. I mean, the concept of machine learning and artificial intelligence is like decades old, right? But we didn't have the computational power to do something with it. Okay, so that's like the precursor to what I really wanted to talk about, and this is how AI and ML are going to converge with HPC and what this implies for containers at the end. This slide I showed last year in a different version, but it's basically still the same. So we have a couple of problems we need to solve. Some are simple, some are more complex. The first one is rather simple. So if you have a single node, like you have your node at AWS or you have your computer at home, and you have simple storage, which is just your block storage on the host, you can easily do machine learning with TensorFlow. You just have to use NVIDIA Docker, or you use some Docker mechanism to map in the hardware underneath, get the correct image from NVIDIA maybe, and then you can run TensorFlow without no big problems. Once your cat and dog pictures are so big that you need to get it from a shared file system like Samba and NFS, but more on HPC is more Lustre and GPFS, so faster things. But anyway, it's a POSIX file system that you want to access in a controlled manner from a container. You are nowadays kind of in trouble because every user can define minus user, and he can say, okay, I'm Alice, even though he's Bob, and then he can access the shared file system on the host as Bob, posing as Bob, and that's not what you want. So there is some need for change that we need to do in order to get this done. And if once we do this, once we can thrift through a lot of cat and dog pictures to create models to detect those two, we might have a model that is too big for one node. So one model that needs more memory than is able to aggregate from one node with a couple of GPUs. So we need to distribute the job. So we need to create a job that spans across multiple nodes to aggregate all the GPU memory. That would be the first technical reason to do it. The second technical reason might be to aggregate the I/O from all the different nodes to the shared file system, the network file system, so that you can go to more pictures in faster time. Or maybe an economical reason would be that one big box with a lot of GPUs, it's crazy expensive. NVIDIA has this DGX2, which costs you $400K, has 16 GPUs acting as one, 30 terabyte of NVRAM. It's like crazy expensive, but it works because it sticks into the single node sample storage paradigm. But if you want to distribute it to commodity hardware, which is much cheaper, where you can with $400K maybe buy 40 GPUs in 40 boxes, then you need to solve this advanced column here. So you have distributed jobs running across multiple nodes. You have data access to shared file system, and in an HPC case, fast shared file system, and you can access the hardware underneath. So you're basically doing HPC anyways, because this is what constitutes HPC. But as said, I want to focus on the beginner stage here, and the first one is to get hardware access. And I think, in my opinion, runtimes, I don't care about runtimes anymore. It has to be the scheduler that decides what hardware to use anyways, because that's where the logic is, how much resources you have and what hardware resources the node has anyway, so there's no need for the runtime to intervene. So there is a thing called the Kubernetes device plugin, which is pretty straightforward. This is an example for GPU use. So this node has 2 GPUs. The device plugin knows about the 2 GPUs because it discovered it. So the container can just say, I want the first GPU, or he wants 1 GPU, and the device plugin says, okay, I give you the first GPU. Then it will map in this NVIDIA 0 device, because this is the one you need to access the first GPU. And they have 2 other devices mapped in. This is auxiliary devices from the kernel driver. In order to control certain things on the GPU, you need them as well in order to make real use of it. And depending on what use case you have, there's some crazy use cases you can do with containers. You need different OS kernel devices. But that's pretty simple. And if a second container comes along and wants also a GPU, and this node has obviously 2, the device plugin can just say, okay, I give you dev NVIDIA 1, I map it in as dev NVIDIA 0, and then the container can use the second GPU without any problems. So that's pretty straightforward. It's like 50 lines of Go code. I wrote one device plugin myself. It's simple. It's not a problem. And before I go into the hardware-specific stuff, I just want to talk briefly about the intermediate thing. That's also not so complicated, I think. So as said, if you map in a shared home file system into 2 containers, the only thing you need to make sure of is that the user ID and the group ID of the process that starts the container is owned by the user that started the container. So if Alice starts a container, the user ID and group ID has to be the one of Alice, and then you have no problem mounting in the home file system. And if it's Bob, then of course it needs to be the user ID and group ID of Bob. The problem, however, is that in most things you can just change the user ID when you start a container. When you start a pod, you can define what user ID you want to have. And that's kind of the challenge here. And also in a couple of bigger environments like big manufacturers, for instance, they have policies that you need to have different users in different environments. So if you have a site in Singapore and you have a site in Hamburg, you will have different user IDs, you will have different usernames, and then mapping this, that's a challenge. But that's like a challenge to be done, but it's not super complicated. Another way of doing it is to use rootless container engines. There's a patch for Docker-D on is already merged. It's in Docker-D now, so that you can start Docker as a rootless engine, which means that the user, if you're a user, you start your own Docker daemon under your user, and if you start a container, then your Docker engine doesn't run as root. It doesn't run with privileges. So you can start containers, and the user that is like starting at this container is also your own user ID, because you own the Docker-D process basically. It misses some functionality, but it's basically kind of nice. But as I said, there needs some more research and experimenting. But that would be another idea of creating your own Docker daemon for a particular user, and you can then go along and access file systems as well. And while we at it, so I would like briefly touch on schedulers. In HPC, we have in non-HPC we have Swarm and Kubernetes, the most dominant one. They are not designed to access shared file systems. They are not designed, like, to some extent they are, like as just shown, the device plugin works, but it's harder to access shared file systems. They will just create a process that is isolated from the host file system, from the host and from each other, and then go along with it. In HPC, it's more deeply integrated. There is a scheduler. One example would be Slurm, who starts processes on behalf of the user, and then the process will just tug along as if the user would have started it himself by SSHing into the box, for instance. Another iteration on this might be in the future that an HPC scheduler will just use the container engine underneath. That would be my hope, and I think we're on a good way. And something else would be that you change the Kubernetes scheduler to an HPC scheduler, have the scheduler logic within Kubernetes as an addition, as a plugin, and then go along with this as well. Problem here is that in HPC you sometimes you want to spawn 1 million jobs at a time, and the Kubernetes API takes like a couple of 100 milliseconds to respond to a creation of a job. And if you want to spawn 1 million jobs and you need 200 milliseconds for one job, then that takes too long. So that's something that needs to be changed. Okay, so first thing about the hardware stuff is that in AI and ML, for instance, and in HPC in general, there are multi-phases of your workflow as a scientist, right? So you first need to provision something that's mostly done by ops guys. Maybe that's not something that you care about. Then if you're a data scientist, you want to use a Jupyter notebook and like tune and train your model, write a little Python in your interactive Jupyter notebook and play around with the data. Once you're fine with what you just created, maybe it's a classifier or whatever, then you want to train it with a lot of data, so you might want to create a batch job out of it so that you can train and plow through a lot of data. And at the end, you want to use this model to do inferencing at scale, so you want to make a service out of it, a microservice that tells you dog, cat, or something else. And in order to do this, you need a modular assembly of the software stack. This is an example of Boston Consulting Group's talk from the DockerCon last year, where they showed how they construct their images. So they have a very composable construction where they have a base image, then they have the domain, which is maybe computer vision or reinforced learning or whatever, which has all the different Python and R packages. On top, they use a framework, so you could choose TensorFlow, Caffe, PyTorch, whatever. And on the very top, we have these different stages, different user applications, like a Jupyter notebook, like training, and like inferencing with an API. So you have composability and workflow, which needs to be tightly coupled and set up in a way that it's easy to model and create new, maybe, domain templates here. But the important piece here for my talk is that they use multiple different images for depending on what the hardware at the end is, right? So they have an Ubuntu image without any GPU capability. Then they have a CUDA 8 and CUDA 9 image, and depending on what host you will land, you will get different images, or you need to use different images in some way for your reinforcement learning Jupyter notebook here, because you need different underlying technologies to be mapped into the container. And that's ugly. Why is it ugly? Because the kernel doesn't know about the kernel bypassing stuff, that is GPUs, that is network cards in some cases, and also the kernel level isolation that we use for containers also doesn't know about the microarchitecture of the CPU, for instance. So if you have a Broadwell CPU or you have a Skylake CPU, you have different optimizations you can use in your code. So you could use vector lengths with AVX 512 of 512 bytes, and you can try to squeeze your code or shake your code in a way that it uses this optimization, and your computation will be much faster. But the container doesn't know about this. The container runtime in particular doesn't know about it. So if you want to optimize for the platform, the only thing you can optimize for is the architecture, which is represented by this GoArch variable. So you can do AMD 64, ARM 64, PowerPC, and so on. So there are only a couple of things that are recognized by the runtime. But what you miss here is the different variants, the different microarchitectures that are provided by the different vendors. So you have, like, as said, Broadwell, Skylake, Kaby Lake, you name it. And all these optimizations are missing when you download an image. You can only download an image that is generic, basically, for your architecture. And how people cope with this is either they create an image that is suitable for everyone, like an Nginx image you download, and it's an AMD 64 binary. It will just run, but it might not be as effective if you would compile it with the optimizations. Or NVIDIA does it a lot. They use an entry point that figures out what is my underlying architecture, GPU architecture, but could also apply to CPU architecture, and then they will decide at runtime what binary to start, or using a fat binary with all the different execution paths in there. You could also have different architectures within the fat binary and then use the optimizations in there. But the problem with this approach is, the second one is that you bloat the image, and it's a runtime decision what you will execute. So you have a big image in the first place, and it's hard to reproduce the outcome because you have different execution paths, and that's also ugly, right? You can do something ugly, which is, I think, okay-ish, but it's still ugly. So you could create different images with different tags or different names. So you have to come up with a naming scheme in the first place. and create a maybe benchmark image for Kaby Lake, a benchmark image for Broadwell, and then let the scheduler decide what to do. So make it not a runtime problem, but more a scheduler or distribution problem. But the problem is that the scheduler then needs to know what host needs what image, and you need to annotate the host with I'm a Broadwell host, and when you schedule something, you need to decide where to put the image. So that's a little bit ugly, and it's going to be painful because the naming scheme you come up with won't be a naming scheme for the future, so it will be somehow break, and that's something that's ugly as well. An example of this current affairs thing is like this. So you might have a benchmark that has different tags for different architectures. And here I have different types, machine types that I define. I have a type 1 with Broadwell, type 3 with Coffee Lake, and a type 4 with a GPU even. And I use different tags to specify different containers or container images that are optimized for certain things. And that's a use case might be a TensorFlow, for instance. Okay, what can be done to some extent is using manifest lists. When you download an Ubuntu image, for instance, due to this GoArch and GoOS variable in the runtime, it will figure out, okay, I'm an AMD 64 host, I'm a Linux host, so I will get the Ubuntu image for Linux for an AMD 64 system. If you're a PowerPC, you will get the other one. And within the OCI specification, you can also pass in or put in features, and these are hardware features that no one really uses, and you could define different images for different systems within the manifest list itself. And as I worked for Docker, I patched the Docker daemon a little bit so that it recognizes different features, and it then at runtime would download the correct image. But when I dropped out, I tried to put it in the open source upstream version, and this was like painful, so I thought maybe there's another way of doing it. And another way of doing it is make it a registry problem, like a distribution problem, and not a runtime problem. So I created MetaHub, which is like a Golang project that allows you to define different machine types. So I have type 1, type 2, type 3, type 4, according to the previous slide, with different architectures. And I create credentials, like a login for the registry for each and every type. So type 1 logs in with type 1 into MetaHub, type 2 logs in with type 2 into MetaHub, and then MetaHub will just trim down the manifest list, looking at the features, to the one that is the best one to serve for the host. So it will just take the manifest list we saw before, look into like the login that is used, and then trim down the correct image. So when the host downloads the manifest list, which is just a short one here, he has no choice but then use the optimized image. And the second one will get another image, and so on. So it will just dynamically create this manifest list and leave the runtime no choice than to download the correct image, which is totally runtime independent. So if you use Rocket, if you use Docker, if you use Cryo, if you use whatever, Singularity or Saros or whatever, this is OCI compliant stuff, so it will work with everything. And if you schedule this with Kubernetes or Swarm or whatever, it will also work. So that's kind of a nice OCI approach, I think. So you log in with different types, and when you download and run the image, it will automatically download the correct image for you, and it will execute it. This is open source, as said. I put it on GitHub, and there is a blog post accompanying it. And that would be the talk. I have like 2 additional slides. You want to do CI/CD in this case, so if you want to come up with all the different images, don't do this by hand. Create something in CI/CD that creates a different variants that you need to create, like cross-compiling for different architectures, and then use something like manifest tool to create the manifest list and push it to your registry. So if you do this by hand, you will go mad. And also, I attended a couple of conferences the last couple of weeks, and we talked about, during beer, of course, how we could come up with simple and sane first iterations on the features we want to figure out, like the CPU Broadwell thing that I showed, and I think some idea about like something from the proc feature, CPU feature, CPU file system would be nice. And we want to pick some examples and use cases where we can show. Maybe also some non-HPC stuff. So if you compile Nginx or FFmpeg for a certain architecture or with certain acceleration features, that could also help the non-HPC world, because you can speed up your workloads as well, and this is something that we don't talk about much. Also for ARM, if you compile it for the right ARM architecture, for the right ARM variant, then you will get much faster and smaller images, and I think that's something that we should use. Okay, and of course, what are the limits? That would be something to think about here. I put it in the frame of hardware, but it could also be like configuration, so you have different hosts and different zones, and you need to configure something slightly different. You could also use this approach to have different images with different pre-configured hosts or images, so that you don't need to choose at runtime and define what you need to do, but you could pre-bake it into an image and then get just the right image. So I think that's also something to think about. Okay, now it's over. Like, that's the second version of the thank you slide. As I said, I attended some conferences. I had a workshop last week where we talked about this kind of stuff for a whole day. So that's a shameless plug of a YouTube playlist, basically, I'm just uploading to.